Hi all, Mike Landry here. In this video, we'll cover how to perform a chi-square and a Fisher's exact test using SPSS. I started off with a data set in Excel that you have access to. I uploaded it to SPSS in a process that was demonstrated in another video. And so I now have a nice data set in SPSS that I can analyze. And for this test, what I want to analyze is gender, which is represented in nominal data where we have 0 means a male, 1 means a female. And I want to look at smoking history where 0 is does not smoke and 1 the participant does smoke. If we were looking at differences between these two groups, males and females, if we had scale data, such as say the BMI or systolic blood pressure, where we have these numbers with equal distances between each level of the number, scale data, we could use an independent samples t-test. If we want to compare gender and say something like obesity, that's ranked here as 0 being underweight, 1 being normal weight, 2 being overweight, and 3 being obese, in other words, ordinal data, we would not be able to use the independent samples t-test. In that case, we would use a Mann-Whitney U. But because we have nominal data in what is our dependent variable, the smoking history, we cannot use the independent samples t-test or the Mann-Whitney U, and so we use the chi-square. So let's see how that works. From the top toolbar, I'll select Analyze. I will go down to Descriptive Statistics and over to Crosstabs. Here you can see I was already running this test earlier, so I'll take that back out, and this is how it would look in SPSS. It doesn't matter when we're doing a chi-square which we choose for rows and columns. I prefer doing it this way. I'll use gender in the rows. I consider that to be my independent variable. And I will look at smoking history as a dependent variable. I'll put that in the columns. There are a few choices here we can make under exact. There's nothing we need to change there. Under statistics, we're going to want to check the chi-square, and we do not need to check the Fishers. That's automatically done in SPSS. Cells are important. Here we see that we do have the choice of observed and expected. I prefer to only check off the observed frequency for a chi-square, because if I check others, it starts to get complicated, and we'll see that in just a moment. But you can check percentages, observed, expected. I prefer just to check off observed. We'll press continue for that. We'll select OK to analyze the data. And now we have 3 tables of output from our chi-square. This first table, all this indicates is that we had 20 participants, and we had none that had missing data. We had 100%. This is not something we would report, other than you would report your N of 20. In terms of the frequency table, you'll notice this is the actual count. You remember I only chose observed. If I chose expected and the percentages, this gets really large and complicated. But let's take a look really carefully at what this means. And by the way, if I was going to copy this and put it into an APA paper, I want to substitute the coding for what it means. Like, in other words, I would put males where the 0 is, females where the 1 is. Under smoking history, I'd put maybe none or does not smoke, and under 1 I would put yes, smokes or smokes. If you notice what these numbers mean, though, what they indicate is that we had 3 males who did not smoke, 6 males who did smoke, and for females we had 9 who did not smoke and 2 that did smoke. The rest of these numbers is simply the sums of these columns and rows, so we have 3 plus 9 is 12, and so forth and so on. And here's our N in the bottom corner, 20. So this looks like we do have some kind of difference going on, where we had 9 of 11 women not smoking and 6 of 9 men who did smoke. That's our frequency table. Under the chi-square table, we have several different ways that chi has been calculated. And I want to go through each of these very quickly. Normally, we would report the Pearson's chi-square. This is the chi value, 4.84, degrees of freedom 1, significance of 0.028, which is below 0.05. So if we were only looking at the Pearsons, we would say that this is significant. We would reject the null, and we would say that there is a difference between males and females on smoking history in the sample. And we could also say that it looks like males tend to smoke more than females in this particular sample. There is a problem, though. We have numbers here in these cells that are below 5. We have too many cells below 5, so we've actually violated the assumptions of the chi-square due to our low sample size. So in those cases, that's when we use the Fisher's exact test. So if you notice for the Fisher's exact test, our significance is a 0.065, which is above 0.05. So this is an indication that we failed to reject the null. We really didn't find a significant difference. And if you wanted to say it's possibly due to the small sample size, I would say that that's a pretty good thought here, because we do have a small sample size and we did know that Pearson's was low. And this would be an indication that we need a larger sample size. Maybe we need to run the study again with a larger sample size. I was asked what these other terms mean, and so I'd like to go over those just really very quickly. First of all, when the Pearson's is calculated, in the old days when I first started taking statistics, we would get the Pearson's number, this 4.84, or the chi value. We would take the degrees of freedom, we would go to a chart, and there we would find our 0.028, our p-value. But as SPSS calculates this for us, these other numbers, even though we report them, are not something we really need to be too concerned about. The chi value, the degrees of freedom, are only numbers that help to interpret what the p-value is. And you can look at one of these charts and find that, for example, the question a student asked was, well, is a 17 better than a 4 on the chi value? And the right response is it all depends on what the degrees of freedom is. So these numbers, if you want to look at it this way, are only valuable in determining our p-value. In calculating a chi-square in this manner, there is a slight error that's always introduced, but because most people report the Pearson's, we understand that, and it's a very small error. But the continuity correction is a way of calculating chi that was come up by Yates. It's actually an overcorrection, and if you notice, using Yates' model, we have a 0.081, and that's actually so high that all other things being equal, we would not be able to reject the null. It's even higher than the Fisher's exact test, which is very conservative. So that's another way of calculating chi proposed by Yates. The likelihood ratio is the third way of reporting chi, and it uses a modeling technique where we look to see if the data more closely approximates a null model or a research hypothesis model, and you'll see that it's very close. It's seldom used, so I would typically encourage you not to report it. The linear by linear association calculates chi by looking at trends. It's good for ordinal data. Again, it's very similar to the Pearson's, but it's seldom reported. So the bottom line here is I actually would not put this table in a paper or in a presentation for the results of this particular study. I would merely report the Pearson's chi-square, the chi-square value, the degrees of freedom, and the p-value. And that has been demonstrated in another video that I provided to you. I hope you found this helpful. We've covered how to perform a Pearson's chi-square as well as the value of the Fisher's exact test. We've covered the other ways in which chi can be calculated, even though they're rarely used. I hope you found this helpful.